Assalamu alaikum everyone. So today we will be having our lecture number 21 and we will be talking about spread spectrum, and here is the overview of the topics which we will be talking about one by one. First of all, introduction of spread spectrum, then the model of spread spectrum, and we will discuss the model while taking into account transmitter and receiver. Then pseudo numbers, pseudo random sequences, they are very important when we talk about spread spectrum. And then the circuitry which is being used in order to generate PN sequence numbers, pseudo noise sequence numbers. And then we have two different types of spread spectrum. First one is direct sequence spread spectrum, and the other one is frequency hopping spread spectrum. So we will be talking about these two different types of spread spectrum techniques. And then the we can gauge the spread by processing gain, and we will be talking about the mathematical representation of processing gain. And then what are the different modulation schemes, and we will be talking one of these modulation scheme, that is binary phase shift keying, which is used when we have direct sequence spread spectrum. So let's start. So its spread spectrum is actually initiated by the military, right? And the fundamental objective was at that time that it is very difficult to intercept, it's very difficult to jam, and that actually characteristic comes ideal for the application whenever we talk about military vehicles, military communication, right? But nowadays this spread spectrum technique is being used for cellular communication. It is also being used for cordless telephony, wireless LANs, and we also having some other area where this technology is being adopted due to its different characteristics. So here we have different characteristics of the underlying spread spectrum. First, it's wideband modulation, and there it carries certain benefits. First of all, as I have mentioned, that it's secure. It's very difficult to tap and intercept, and it's very much immune to interference. And then it is sharing different bands. Then we can have different types of spread spectrum, and we have frequency hopping spread spectrum. So the features of the underlying frequency hopping spread spectrum is that data are constant, frequencies are randomized, right? Whenever we talk about the other category of spread spectrum, here we have frequency is constant and the data is randomized, right? So you can feel the difference, and it's more immune to noise. And we have multipath fading when we talk about normal conventional communication. So it is also very immune to multipath fading and distortion. We can hide and encrypt signals, and several users can share same higher bandwidth with little interference. CDM and CDMA are one of the applications. Right. So as mentioned, that this communication encoding scheme is widely accepted and is being used widely for different technologies, and wireless communication is one of the technology where the underlying spread spectrum is being used. And we have analog and digital data with analog signaling. So whenever we can represent, we can have the provision of analog signaling, right, irrespective of the data representation. So data representation can either be analog and it can be digital. So in both cases we can use this analog signaling technique. So it spreads data over wide bands, and it's very difficult for jammers and interceptors, right? So we have two approaches I've mentioned. One is frequency hopping and the other one is direct sequence. So here, if we talk about the communication system, so we have a transmitter. So the information has to be transmitted by using some channel, and that channel or that medium can be a free space, right? And it can be wired media or guided media. Then we have a fiber optics that uses light in order to transmit information from one point to another point, and it's a high-speed link. And we can also have different other media like UTP and STP and coaxial cable. So here is the communication channel between the transmitter and the receiver, and of course those channels, they introduce noise. So on the receiver side we have to detect the information intelligently. So here is the general model of spectrum. So here we have the input data, and then after we have the channel encoder block, so that is performing the channel encoding, and then we have to modulate the data in order to transmit the data over the channel, and this is the channel. Then we have to perform the operations which are being performed on the transmitter side in reverse order. So here you can see last one is modulation. So on the receiver side we will be performing demodulation first, right? So this is the last, and here this is the first, and then we have to perform the channel decoding. And you can see that this here while we are modulating, we are having spreading code over here, and here again when we are performing demodulation, so it's you can say de-spreading code over here, right? So pseudo noise generator, and you can see pseudo noise generator again here, and we will be talk in more details how we can do that, right? Okay, so let's talk about the pseudo sequences or pseudo noise generator. The spread of the random sequence of frequencies is determined by the pseudo noise sequence generator, right? So what this pseudo noise generator is, generator outputs a stream of bits, ones and zeros, that appears random, has no apparent pattern, right? So it generates a pattern randomly, so it's not completely random. That's why we have mentioned pseudo random. Sequence generators are easy to construct using simple logic components. So we can use XOR gates, a shift register made up of flip-flops. A PN sequence is not truly random, so that's why we are having pseudo random, and it's periodic and repeats at fixed interval of time. So generated by a deterministic algorithm, so not actually random, but if algorithm is good, so it is actually reasonable. So we have to start with an initial seed, right, and need to know algorithm and seed to predict sequence. So this due to this seed, right, and the prefixed algorithm that is being set up between transmitter and receiver, so only receiver can decode the signal. So this is one of the advantage of the PN sequence, right? So PN sequence generator, number of iterations before the sequence repeats. So the length of the PN sequence is equal to or can be measured before the sequence repeats itself, right? So length is, we can establish a formula, number of flip-flops, n in the shift register, and selection of feedback taps that are applied to one or more XOR gates. The sequence length, here we are going to calculate the length of the sequence, right? So minimum PN sequence length is 2 raised to power n minus 1, where n is the number of flip-flops. So a sequence that has this length is said to be a maximal length sequence. So here we have a PN sequence generator, right? So you can see the number of flip-flops are 3. So 2 raised to power n, so this n should be in the par. So it should not be here, it should be here. Minus 1. So again 2 raised to power 3 minus 1, so 8 minus 1 is equal to 7, right? And you can see 3 flip-flops are here, and they are being 2 of them being XORed, and here we have the feedback. So this is the clock, right? And you can calculate, or you can have the truth table for this circuitry. So here we have the example is a maximal length PN sequence generator. So how many outputs, ones and zeros, would it produce before the sequence repeats, right? So here are the calculations. So it's very simple. So we have this is the PN code output 1, 2, 3, 4, 5. So we have the formula 2 raised to power n minus 1, where n is the number of flip-flops. So we have 5 flip-flops over here. So you can have 2 raised to power 5 minus 1, so that amounts to 31, right? So it's 32 minus 1, 31. So we have the maximal length of the sequence before it repeats again, right? So as mentioned, that while we talk about, or we have to use spread spectrum, so we can have 2 different types of techniques. First one is frequency hopping. Signal is broadcast over seemingly random series of frequencies. Receiver hops between frequencies in synchronization with transmitter. So there should be a synchronization between receiver and transmitter, and it's very difficult for the eavesdropper and jammers to affect the communication, right? So this is one of the advantage of the frequency hopping spread spectrum, dictated by spreading code, receiver hopping between frequencies in synchronization with transmitter, picks up message. So again, life is very difficult for interceptor, jammers, eavesdropper. So here we have the graphical representation of frequency hopping. So you can see we have the frequency axis, and here is the energy, right? So you can see F1, F2, so channel assignment, and then we have spread the frequency. You can see this is the time and this is the frequency. So we have, so here is the transmitter design for frequency hopping spread spectrum. So you can see binary data modulator, and we can use FSK or binary phase shift keying, frequency shift keying or binary phase shift keying. And after the modulation, here we have the modulated data, and here is the spreader, right? So this is the spreader. So you can see in the spreader we have the multiplier, right? And here we have the pseudo noise bit source, channel table, frequency synthesizer, and this is here we have the CT and this modulated signal, and they are multiplied, and this is the band pass filter, right? And we are actually having the spread spectrum signal over here, and This is the transmitter design. So as we all know that transmitter, it's easy to transmit the data, but it's difficult to receive or extract the information from the receiver side whenever we talk about the data transmission. So receiver has to struggle or has to work a lot in order to extract the original data because of noise and some other metrics, right? So here you can see that we have the receiver design. So as mentioned, this has to be, the operations has to be reversed, right? So here we have the modulation first, and then if you can see hopping spreader last. So again, on the receiver side, this is the received signal after from the channel. So first we have the despreader, right? So pseudo noise bit source, so it has to be synchronized. As transmitter and receiver, they are synchronized and they know that what sort of pseudo noise bit source they have to, right? And then we have the channel table, and frequency synthesizer, and after that we have the band pass filter, right, and the modulator, and we will be having the original data, right? And then we have different types of frequency hopping spread spectrum, slow and fast. Commonly use multiple FSK, MFSK, have frequency shifted every TC, and duration of signal element is TS, and slow frequency hopping spread spectrum has TC greater or equal to TS. For fast, we have a different scenario, TC is less than TS. So frequency hopping spread spectrum, it's quite immune to noise and jamming. And then we also have slow and fast MFSK frequency hopping spread spectrum, so you can have the graphical interpretation of the underlying types of frequency hopping spread spectrum. So here we have considered some of the performance characteristics of the frequency hopping spread spectrum. So large number of frequencies are used, and it results in a system that is quite resistant to jamming, right? So jammers must jam all frequencies, which is not the case. So in that case, if they are jamming all the frequencies, so it can affect their own frequency on which they are transmitting and receiving. This reduces the jamming power in any one frequency band. And then we have another type of spread spectrum, that is direct sequence spread spectrum. Each bit is represented by multiple bits using a spreading code. This spreads signal across a wide frequency band, and it has the same performance as that of the frequency hopping spread spectrum. So here we have message bit stream is modified by a high rate pseudo noise sequence generator called a chip sequence, right? So let me explain the functionality of this OR gate over here, right? So let's wait for some slide, then we will talk about the functionality of XOR and the property of the XOR that is being exploited over here in order to have the chipping sequence, right? And the data and this PSN chipping sequence, PSN code generator, they are XORed, and why they are XORed. So serial binary data, right? And here we have the PSN code generator, and they are XORed, and then we are modulating BPSK, binary phase shift keying modulator, and this is the carrier, and then we have the power amplifier, and there is the antenna, and we have radiated the corresponding EM wave into the free space. direct sequence spread spectrum, the serial binary data is ZOD with pseudo-random binary code. So this is the pseudo-random binary code which has a bit rate faster than the binary data rate, and the result is used to phase modulate a carrier. So chipping rate, bit rate of the pseudo-random code, this is chipping rate. The faster you change the phase of a carrier, the more bandwidth the signal takes up. Looks like noise. So here we have the flow graph, or you can say the timing diagram for direct sequence spread spectrum, and you can see this is the data, time of one data bit, 1 1 0 1, and here we have the carrier, right, carrier modulated by the data, right. So you can see the modulation, right, phase shift keying, binary phase shift keying whenever we have a 1, so there is a phase shift, and here again 1, so no phase shift, 1 1, and here we have 0 phase shift, 1 again phase shift. So this is the pseudo random sequence, and you can see, or this can also be regarded as the chipping code, and this is the data plus pseudo random sequence, right. So you can see we have, so here is the data, right, so 1 1 0 1, and you can see 1, and here we have 1. So let me write down the truth table for the XOR gate, right. So we know if we have two inputs X and Y for the XOR gate, so 0 0 0 1 1 0 and 1 1, right. So this is 0 when both inputs are same, XOR produces 0. So any one of the input, either X or Y, are 1, then we have a 1 1, and again two inputs are same, so we have a 0, right. So we can look at the implement truth table. So this is the, let me mention or write down, so this is the truth table for XOR. So I can also mention this, so this can be the, right. So let's apply the truth table over here, 1, and here this is the pseudo random sequence, so see 0, and here we have 1, this is 1, right. So 1 1, again 0, and 1 0 1, so again this will be 1 1, so it will be 0, so is 1, and you can see that we have the implementation, right. So you can see that now we are actually having the carrier modulated by the data plus PRS. So here we have the carrier that is modulated by data only, and here we have the carrier that is modulated by the data plus PRS, right. So this is the resultant or the XOR operation of, right. So let me give you an example why we are using XOR over here. 1 1 0 1, right. So this is the data, and here let me randomly choose So this is the, let's assume PRS. So I am performing the XOR 1 0 0 0. So we have the XOR operation between the data, so that is the data, and here we have the XOR operation, right, and this is the resultant, right. So if I have to retrieve the data, so what I can do, because both the transmitter and the receiver, they know the pseudo random sequence. So 1 0 1 1. So this is what. So you can say that if this is the resultant and then this resultant is transmitted by using some channel, and here we have the receiver, right, and receiver received and then received signal or received bits, and then those received bits are XORed with again the pseudo random sequence. And what is this? So this is the data, original data that we are actually interested in, and we want to retrieve the data, right? So here again, I'm not including this part, that is the carrier modulated by the data, and then after the XORed operation of PS pseudo random sequence with the data, then we again have modulated the resultant with the carrier, right? So you can see here we have the output after data plus PRS XOR operation. So you can see 1, and here is we have a phase shift, right? So again 1 phase shift, and whenever we have, okay, so here we have some of the observations. A signal that would normally occupy a few kilohertz bandwidth, right? So now it's spread out 10 to 10,000 times, right? Its bandwidth. The fast phase modulation spreads the energy of the signal over a wide band, right? Appears as noise in conventional receiver. Also, it's also called CDMA, code division multiple access, and it's this technology is being used in satellites. Many signals can use the same transponder used in cellular communication, many users in the same bandwidth, right? So if we talk about the receiver, pseudo, so as mentioned, so I have mentioned here that if we know the pseudo random sequence, then we are able to retrieve the data. Must know the pseudo random sequence of the transmitter and have a synchronization circuitry to get in step with this pseudo random digital signal. Identically programmed PN sequence compares incoming signals and picks out the one with the highest correlation, right? So we have to take the correlation. Other signals using different PN sequence appears as noise to the receiver, and they are not recognized. Then we can measure the or we can gauge the spreading by the processing gain, right? So this processing gain is represented mathematically by G, and we have the expression for this processing gain, bandwidth over FB, where BW is the bandwidth and data rate that is being represented by the FB. The higher the processing gain, the greater the spreading is, right? So the greater the DSSS signal's ability to fight interference. Right, so here we have the example. So we have the information signal is 13 kilobits per second spread over 1.2 megahertz. So you can see the difference. So this is 13 kilobits per second, and now you can see the shift towards the higher frequency, 1.25 megahertz. Right, so 1.25 megahertz, this is the data rate. And you can see the higher the gain, the greater the system's ability to fight the interference, right? So if I have to convert this into dBs, so we will be taking 10 log 96.15, and it comes out 19.83 dB. So here we have the example for direct sequence spread spectrum. So you can see we have the input data. So this is the locally generated PN bit stream, right? So pseudo noise bit stream, and this is the transmitted signal, and we have performed XORD. C is equal to A is XORD with B. A is the input data and B is the locally generated PN bit stream. And then this is on the transmitter side, and this transmitter will be sending signal to the receiver and receiver side. So here we have the received signal. So again you can see the synchronization between PN bit stream. So PN bit stream between transmitter and receiver, it is the same, right? So let me mark, and here you can see this one, and this one, right? So they are the same, right? So this is the same which I have explained, and you can see that. So again, let me mention for your understanding that we have X, Y, and this is the output, and this is the truth table for XOR 0 0 0 0 1 1 1 0 1 and 1 1 0, right? So now you can calculate, and you can see that here we have the input data. So again 0 is represented by this level and 1 is represented by another level. And this is the width of the bit that is represented by T, and you can see 0, right? So this all is 0, and 0 0 we have 0, right? And 0 1 1 0 1 1, right? And here we have 0 0, it's 0, and now we have 0 1 0 and 0 0 1. So this is 1. So I pronounce is wrongly. So this is 1 1 1 0. Again 1 will continue for this bit time slot, and here 1 0 1 1 0 1, right? 1 1 0, and this is now 0 0 0 0 1 1 0 1 1, right? So and so forth. So you can use this truth table in order to calculate this, and this signal is the transmitted signal. And then on the other side we have the received signal, and the received signal is XORed again with the same locally generated PN number stream, and you can see that this is the data output, right? So again let me calculate first few, right? 0 0 0 1 1 0 1 1 0 and 0 0 0. So this is 0, right? So here 1 0 1, right? So this is 1, and then 1 0 again 1, right? And 1 0 again 1, and 1 0 again 1. So this is all 1, and here we have 0 0 0 1 1 0 1 1 0 and 0 0 0, right? So this all is 0, and again 1 1 0 0 0 0 1 1 0 1 1 0. So you can see that this one and this one. So this is the transmitted data, right? This is the input data, and here we have extracted the original data. So here we have the circuitry for the direct sequence spread spectrum. So you can see we have transmitter and receiver. So binary data, right? So the modulation is performed first over here. So if I go back, so you can see this is the circuitry for the frequency hopping spectrum, again here modulation, then the frequency hopping circuitry. So right, so here we have the binary data, and you can see the modulator, and it's using binary phase shift keying, and this is the modulated signal, and this is the direct sequence spreader, pseudo noise bit source. It is generating the PN bit stream, and then bit stream is has to be multiplied with this signal, and then we have the spectrum transmission over the channel, D-spreader, right, and pseudo noise bit source. So they has to be synchronized, and then demodulator, right. So again it's the same, using binary phase shift keying. So you can see that here we have data, and then this is the modulation, right, and this is the spreading code, right, and here we have the modulated signal, right. So you can see the spectrum approximation. So this is signal energy, and here we have the pseudo noise signal spectrum, and here we have the spectrum of the combined signals, CDMA. So it's a multiplexing technique used with spectrum data signal rate D, break each bit into K chips according to a fixed chipping code specific to each user. So that results in a new channel, right, and at a data rate of KD chips per second. So multiple channels can be superimposed. So here we have the CDMA example code, and this is user A, and we have to encode this message, that is 1101, right. So user B, and this is the encoded message, right, and then user C, and we have the this is the code and encoded message. So CDMA for direct sequence spectrum, so data 1, data 2, data 3, and we have these are the carriers, local carriers, right, for modulation, and then we have the, right, so here you can see we have modulation at 2 steps, right. So here we again have a modulation, right, so that's why we are having 2 modulations over here, and then we have the transmission, and this is the reception. So here we will be talking about more details regarding spectrum. So it's secure communications. There are a number of reasons why we call it or name it a secure communication. One of the reasons is that it uses a wideband noise-like signals, and those sort of signals, they are very difficult to detect, and it's very hard to intercept them. And if you want to construct the circuitry, or you want to have the system that can demodulate after capturing the signal, so those signals, they might be the raw data you cannot understand, so you cannot demodulate in order to have or in order to extract the data. So that's why they are very hard to detect, intercept, and modulate, right. So moreover, they are very harder to jam, right. So if somebody want to jam, so they have to jam all the band, so that's not possible. And there is these low probability of intercept and anti-jamming features. They make this technique ideal for the military purpose. Okay, then if we talk about the spectral density, so spectrum transmitters use similar transmit power levels narrowband transmitters. So as a result, the signals are so wide that they transmit at a much lower spectral power density, and this you can say this power density is in watts per hertz than narrowband transmitters. So this lower transmitted power density characteristic, it appears that it make the SPECT spectrum a big plus, right, for the underlying communication system. So there can be another characteristic, that the SPECT spectrum and the narrowband signals, they can occupy the same band with little or no interference. So there can be very little chance of interference. This capability is the main reason for all the interest in the SPECT spectrum today. So the use of special pseudo-noise codes, they make spectrum very close to the noise-like appearance. So that's why they are very hard to detect, intercept and demodulate. So they are providing a very low probability of interception. SPECT spectrum signals, they are hard to detect on narrowband equipment because the signal's energy is spread over a band of maybe 100 times the information bandwidth, right? So we are actually spreading the spectrum. So here we have the graphical representation of the SPECT spectrum spread across a wide band, making them difficult to intercept, modulate and intercept, right? So you can see power on the vertical axis, and here on the horizontal axis we have the frequency, and this is the spread spectrum signal after spreading, and narrowband information signal before spreading. So this is the signal, and after spreading you can see this is a very little band, and after spreading we have a wide band representation. So the spread of energy over a wide band makes spectrum signals less likely to interfere with narrowband communications. So narrowband communications conversely cause little or no interference to spectrum systems because the correlation receiver effectively integrates over a wide bandwidth to recover a spectrum signal. The correlator then spreads out a narrowband interferer over the receiver's total detection bandwidth. Moreover, the total integrated signal density, or SNR, that is signal to noise ratio, at the correlator's input, that is actually the factor that which has to determine whether there will be an interference or not. So all spectrum systems have a threshold or tolerance level of interference beyond which useful communication ceases. So this tolerance or threshold is related to the spectrum processing gain, which is essentially the ratio of the RF bandwidth to the information bandwidth. And we have two different types of spectrum that is already mentioned. Then we have DSSS and CDMA, and here we have the graphical representation of the power density, right? So here you can see that the narrowband signal and the SPECT spectrum signal. So this is the narrowband signal and this is the SPECT spectrum signal. They both are using the same amount of transmission power and carry the same information. So they are carrying the same information by using the same transmission power, but the power density of the SPECT spectrum is on the lower side as opposed to the narrowband signal. So this results in more difficult detection of the presence of the spectrum signal is the amount of power over a certain frequency, right? So if we talk about the receiver end, so you can see at the receiving end of a direct sequence system, the spectrum signal is despreaded. So this is the spreaded signal, and this is the despreaded signal and despread jammer to generate the original narrowband signal. So here we have mentioned the interference, right? So we have shown actually the reason why the spread spectrum technology is more immune to interference. So you can see that if there is an interference jammer in the same band, it will be spread out during the despreading process. So as a result, the impact of the jammer is greatly reduced. So that's why sequence spread spectrum radio fights the interference, right? The transmitter and receiver should be synchronized in order to perform the despreading process correctly, right? So this despreading process requires the synchronization of transmitter and receiver, right? Sequence with the transmitter, right? So they require a receiver to synchronize its sequences with the transmitter sequence via some sort of timing search process. So this looks like a drawback, right? So this drawback is exploited in order to have to take some of the benefits, right? So if the sequences of the multiple transmitters are synchronized with each other, the relative synchronization must make between them can be used to determine relative timing, and that relative timing can be used to calculate the receiver's position, and that actually is the mechanism which is being used for the global positioning system. So we need 3 satellites that are used in order to calculate the position. So process gain, so as mentioned, the amount of spreading depends upon the process gain. Enhancing signal to noise ratio on the channel is called process gain. This effect can be made larger by employing a longer PN sequence, right? So we can have longer PN sequence, right? So in that case, we can increase the signal to noise ratio, right? And more chips per bit. But physical devices used to generate the PN sequence impose practical limits on attainable processing gain. So here, jamming, hopping, and then time and frequency synchronization, right? And frequency parking, and we also have multipath fading when we talk about the communication, especially the wireless communications. The frequency hopper is better than the direct sequence radio when dealing with the multipath fading. Does not stay at the same frequency, and a null at one frequency is usually not a null at another frequency if it is not too close to the original frequency. Deal with the multipath fading issue better than the direct sequence. The frequency hopper, there can be a use case when we have a frequency hopper itself that can suffer performance problems if there is an interference of the underlying frequency hopper with another radio, right? So in that case, the system that survives that can bear the maximum loss, or that can bear the more data loss, it will be the survival one, right? So a voice system can survive an error rate as high as 10 to the power minus 2, while a data system must have an error rate better than 10 to the power minus 4. So voice system here, we can conclude that the voice system can tolerate more as opposed to the data, because the human brain can get in between, right? So if we have a break, so we can understand the communication. So modulation and demodulation, and then we have clock modulation, we also balanced modulation, and there are some of the demodulation steps. Once the signal is coded, modulated, and then sent, the receiver must demodulate the signal in 2 steps. The first step entails removing the spectrum spreading modulation, then the remaining information bearing signal is demodulated by multiplying with a local reference identical to structure and synchronized with the receiver received signal. Okay, we have different coding techniques, right? So codes in a spread spectrum system are used for protection against interference and then provision for privacy and noise effect reduction. So as we know that the errors has to be there. We can have errors when we are transmitting data from transmitter to receiver, so there should be some error detection and correction mechanism, right? So must be used in frequency hopping system in order to overcome the high rates of error induced by partial band jamming. In direct sequence systems, EDACs may not be. Error detection and correction codes may not be advisable because of the effect on the code that increases the apparent data transmission rate and may increase jamming threshold, right? So here we have some of the advantages of spread spectrum: reduced crosstalk interference and better voice quality, data integrity, and less static noise. Lowered susceptibility to multipath fading, so they offer lower multipath fading. Inherent, they are actually built for providing native security natively. They can coexist, longer operating distances, and they are hard to detect, hard to intercept, modulate, and harder to jam. Right, so that's all for today's lecture. So today we have talked about spread spectrum, and we have also discussed the model that is used in order to have the spread spectrum technology, and then we have two different types of techniques that are being used in order to implement the underlying spread spectrum technique. First, we have the frequency hopping spread spectrum, and then we have the direct sequence spread spectrum, and then we also discussed about CDMA, code division multiple access, and finally we talked about different benefits of the spread spectrum. So that's all. आज के लिए इतना ही काफ़ी है मेरी तरफ से. अल्लाह हाफिज़, अपना ख्याल रखिएगा. अस्सलाम वालेकुम.